Okay, hello everybody. Normally you see me do analyzer videos, and that's kind of my specialty, but where I started out was instrumentation. And pretty much most analyzer technicians start off as instrument techs and then move their way up and then gradually get into analytical. I wanted to go back to my roots a little bit, and I wanted to discuss a differential pressure transmitter. Differential pressure transmitters can be used on all sorts of things, as far as you see them on flows across an orifice plate, you'll see them on levels. You'll use this as a differential pressure across a column, so when you see your column start plugging. Alright, so let's discuss the actual parts of the transmitter. You're going to have a diaphragm on each side, and you're going to have a high and a low. So your transmitter will be marked, and it will tell you that it has the high side, and you got your high side and low side. This is going to be my high side, and we're going to be pressuring up the high side. We have our pressure pump, we have a fluke, we have a module that will be measuring the pressure that we're asserting. Our transmitter is on, and it's showing a differential of 0.3 inches of water. This particular transmitter is calibrated 0 to 100 inches of water, non-square rooted. So if you were going to use this for a flow, you would square root it in the DCS. Right, so in order to calibrate this transmitter, we're first going to have some test equipment. In this case, we're going to be using a Fluke 744 to measure our milliamps and also to measure the pressure that we're going to be inserting onto this transmitter. We have a 24-volt power supply. That's what always is used for these transmitters out in the field. And now let's set up the Fluke for measuring the milliamps and the pressure. So the first thing we're going to want to do is we're going to want to source the pressure and measure for milliamps. So as soon as we turn it on, this is how it comes up in the measure mode. So we are measuring milliamps. I got a 4.057. Now we're going to say measure source, and that's going to take us to our source, and we're going to say pressure. So our pressure pump is connected up. We're reading 1.4 inches of water. All right, so we're showing 1.4 inches of water. We're open to atmospheric pressure, so everything should be 0. So while we're here, let's go ahead and just 0. We're showing 0 inches of water there. If we hit measure source, so we're seeing 4 milliamps off the transmitter, 0 inches of water going to our module. We have it open here. We're reading 0.1 inches of water on the transmitter. 0.1 differential. Now, we will connect everybody up. Okay, I've blocked in this, so the only air that is in here is what was at atmospheric pressure. I've tied everything together, so we're all nice and tight. So let's add some pressure. This transmitter is calibrated 0 to 100 inches. (62.8), 14 milliamps. I'm seeing 62.6 on here. We overshot. We're at 111. So we'll take our knob. We'll bring her down. And this just sucks back off some of the pressure yet. You can add pressure, you can pull pressure off. 100.2 inches of water, 20.005 milliamps. 20 milliamps is 100%. 100 inches of water. Alright, so 2.4, 4 milliamps, 0. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 4 is 0, 20 is 100%. So, what is 12? 50%. 50 inches of water, 12 milliamps. So this transmitter is working perfectly. We're calibrated 0 to 100 inches of water. But what I need you to understand is that it's a differential pressure transmitter. And so in order to do that, I want to equalize the pressure to both sides here. All right, so we have, let's throw some pressure on there. A couple of 100 inches of water, and we maxed out. We maxed our transmitter out. It's way above the 20 milliamps. It's saying I'm way over my 100 inches of water span. Now I'm going to open this little needle valve. Look at what my milliamps are doing. We still have a whole bunch of pressure applied to this whole thing. The only difference is we're applying 131 inches of water to both the high side and the low side, giving us a differential of nada. So the exact same thing happens if this transmitter's right here and you have a control valve down here and they're pushing a flow this way across an orifice plate. If you shut the valve, then you're just going to build up pressure on both sides of that orifice plate going down the tubes into your high and low side of your transmitter, giving a differential pressure of 0. As soon as you start opening that valve, flow starts coming through, and when it starts coming through that orifice plate, it makes a massive differential on the high and low side of that transmitter. Now, what happens if we block the low side in and then just bleed everything off? So right now, we have 4 milliamps, differential pressure of 0. We have 130 inches going to both sides. So let's block in the low side and trap that over there and bleed off the high side. Does it make sense? Say yes, it makes sense. Yes, it makes sense. Now, I'll open you up and we will bleed off through here. Okay, so what did we learn on this? Differential pressure transmitter, if you put the same amount of pressure on each side of the transmitter, 0 differential, so you're going to have a 0 output. Our output, I think we'll talk about the output just real quick here. We're sending a 4 to 20 milliamp signal out to the DCS. The DCS is giving us 24 volt power supply. Now, that 24 volts allows us to send back that signal, and it's going to go to a 1 to 5 volts across a 250 ohm resistor once it gets in there. I don't want to get way off in the weeds here, but let's just break down the terminology on talking to the DCS. Okay, so we're going to say that our differential pressure transmitter that we were just looking at was a flow transmitter. And that flow transmitter, so you got 4 to 20 milliamps that's going to be sending the signal to the DCS. 0, 25, 50, 75, 100% to the DCS. The DCS is going to take that and say that's 0 to 20,000 gallons per minute. So 0 to 20,000 gallons per minute. So the thing is, on flows, is you got to square root them. 25% becomes 50, 50% becomes 70.1, 75 is like 87%. So you got to square root them, and then that 0 to 20,000 gallons per minute, what the DCS actually in its terminology is going to be. So we need 50% of 20,000, so we're looking at 10 right here. 70%, da-da-da-da-da. Do the math. I'm not doing it for you. But that is the breakdown on what this transmitter will be talking to the DCS and telling it what it's seeing. Then, of course, the DCS, the distributed control system, is going to tell the control valve, slow down, speed up, give me more, give me less, and control everything in this aspect. Does that make sense? Okay.